Hello everyone. Imagine you are traveling from Colombo to Kandy using Google Maps. There are many different roads you can take. Some roads are longer, some are shorter, and some way have heavy traffic. Have you ever wondered how Google Maps finds the best route so quickly? The answer is through shortest path algorithms. One of the most famous shortest path algorithms is Dijkstra's algorithm. Today I will explain how Dijkstra's algorithm works and why it is important in computer science. Before we begin, let's look at what we will learn today. By the end of this presentation, you will understand what Dijkstra's algorithm is, why it is used, what edge weights means, how distances are updated, a step by step example, why negative weights are not allowed, real world application. Let's it start with the basics. To understand Dijkstra's algorithm, we first need to understand graphs. A graph is a data structure made up of nodes and edges. Nodes are points or locations. Edges are connection between those locations. For example, cities connected by roads can be represented as graph. Social media networks can also be represented as graphs where people are connected to friends. In this example, A, B, C, and D are nodes, and the lines connecting them are edges. Dijkstra's algorithm works on these types of graphs. Now, let's define Dijkstra's algorithm. Dijkstra's algorithm is used to find the shortest path from one starting node to all other nodes in a graph. The graph must have weights assigned to its edges. These weights can represent distance, cost, or travel time. The algorithm starts from a source node and gradually discovers the shortest path to every other node. Instead of checking every possible route, it uses a smart strategy uh, to find the answer efficiently. Now, let's look at the person behind the algorithm. Dijkstra's algorithm was created by Dutch computer scientist Dijkstra W. Dijkstra. He introduced this algorithm in 1956. What is amazing is that he developed it without modern computers. Today, more than 60 years later, his algorithm is still being used in navigation system, computer networks, and software applications around the world. This shows how powerful and important the algorithm is. Why do we use Dijkstra's algorithm? Its main purpose is to find the shortest route between locations. Finding the shortest route helps save time, distance, fuel, money. For example, Google Maps uses shortest path algorithms to suggest routes. Routers use similar algorithms to send data efficiently. Delivery companies use shortest path to calculation to reduce transportation costs. Without shortest path algorithms, these systems would be more slower and less efficient. Now let's discuss edge weights. Edge weights are numbers assigned to the connections between nodes. These numbers can represent different things depending on the situation. For example, a weight could represent distance in kilometers. It could represent travel time in minutes, or it could represent transportation cost. In this graph, the number 2, 4, and 5 are age weights. Dijkstra algorithm uses this value to determine the best route. Let's understand the basic process of Dijkstra's algorithm. The first step is selecting a source node. The source node receives a distant value 0. Every other node receives infinity because their distance are not yet found. The algorithm then visits the nearest unvisited node. After visiting a node, it updates distances of neighboring nodes. This process repeats until every node has been visited. Although these steps seem simple, they are very effective for finding shortest path. Now let's see a practical example. In this graph, node A is our starting point. The numbers on the connection represent travel costs or distances. Our goal is to find the shortest path from A to all other nodes. And as we move through the next slides, watch how the distance change. At the beginning, we assign distance values. Since A is the starting point, its distance is 0. The distance to B, C, and D are set to infinity. Infinity simply means that we do not know how to reach them yet. This is the starting condition of the algorithm. Now we visit node A. We check all nodes directly connect to A. So you can see the distance from A to B is 4. The distance from A to C is 2. The distance from A to D is 5. So we update our table using these values. At this stage, these are the shortest distance we know, right? Next, we look for the node with the smallest distance between B, C, and D. Node C has the smallest value, which is 2. So, C becomes the next node to visit. This is the key idea behind the Dijkstra's algorithm. It always chooses the nearest unvisited node first. This strategy helps the algorithm find shortest paths efficiently. After visiting C, we examine its neighboring nodes. We calculate whether traveling through C gives us shorter route. If the shorter route is found, we update the distance table. This process is called relaxation. The algorithm continuously compares all distance with a newly discovered distance and keeps the smallest value. This is how the shortest paths are gradually discovered. After all nodes have been processed, the algorithm finishes. The final table shows the shortest distance from node A. These values represent the most efficient paths available because every possible improvement has been checked. These are the shortest paths in the graph. One important limitation of Dijkstra's algorithm is that it does not work correctly with negative weights. A negative weight means a path can reduce the total cost. This can cause the algorithm to make incorrect decisions. Dijkstra's algorithm assumes that once the shortest distance is chosen, it will never become smaller. Negative values break this assumption. For graphs with the negative weight, another algorithm called Bellman fold is usually used. Now let's look at some real-world application. GPS navigation systems use shortest path algorithms to find routes. Google Maps uses shortest path calculation to suggest directions. Computer networks use similar techniques to route data. Logistics companies use shortest path algorithm to optimize deliveries. This application demonstrates how uh, Dijkstra's algorithms help solve real-world problems every day. Let's briefly discuss efficiency. Time complexity tells us how fast an algorithm runs as the graph grows larger. A simple implementation of Dijkstra's algorithm has a time complexity of big O of V square. Using a priority queue improves the performance to big O of V plus E log V. This makes the algorithm suitable even for large networks with many nodes and connections. To conclude, Dijkstra's algorithm is one of the most important graph algorithms in computer science. It helps find the shortest path between locations. It uses edge weight to compare routes. It updates distances step by step until the best paths are found. Although it cannot handle negative weights, it remains one of the most widely used shortest path algorithms today. I hope this presentation helped you understand Dijkstra's algorithm in a simple and practical way. Thank you for listening.